given that alpha and beta are the roots of the quadratic equation. Open parent close parent equals a dot x squared plus x plus c. Concepts and formulas. Sum and product of roots. Vieta's theorem. If alpha and beta are the roots of the quadratic equation a dot x squared plus x plus equals 0, then sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals c over a. Useful identities. Alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Alpha cubed plus beta cubed equals open parent alpha plus beta close parent open parent alpha squared minus alpha beta plus beta squared close parent. Alpha over beta plus beta over alpha equals numerator. Alpha squared plus beta squared and numerator over alpha beta alpha squared over beta plus beta squared over alpha equals open parent alpha plus beta close parent dot alpha over beta. 1 over alpha cubed plus 1 over beta cubed equals numerator. Alpha cubed plus beta cubed and numerator over denominator. Alpha cubed, beta cubed, and denominator stepwise solutions. Alpha squared plus beta squared. Using the identity, alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Substituting the values from Vieta's formulas. Alpha squared plus beta squared equals open parent minus b over a. Close parent squared minus 2 open parent c over a. Close parent equals squared over a squared minus 2c over a. 2. Alpha over beta plus beta over alpha using the identity. Alpha over beta plus beta over alpha equals numerator. Alpha squared plus beta squared and numerator over alpha beta substituting values. Alpha over beta plus beta over alpha equals numerator. B squared over a squared minus 2c over a and numerator over denominator. C over a and denominator equals numerator. B squared minus 2ac and numerator over c. 3. Alpha cubed plus beta cubed using the identity. Alpha cubed plus beta cubed equals open parent alpha plus beta close parent open parent alpha squared minus alpha beta plus beta squared close parent. Since alpha squared minus alpha beta plus beta squared equals open parent alpha plus beta close parent squared minus 3 alpha beta. Substituting values. Alpha cubed plus beta cubed equals open parent minus b over a. Close parent open parent b squared over a squared minus 3c over a. Close parent equals minus b over a dot open parent numerator. B squared minus 3ac and numerator over a squared. Close parent equals minus numerator. B open parent b squared minus 3ac close parent and numerator over a cubed. 4. 1 over alpha cubed plus 1 over beta cubed using the identity. 1 over alpha cubed plus 1 over beta cubed equals numerator. Alpha cubed plus beta cubed and numerator over denominator. Alpha cubed, beta cubed, and denominator. Since alpha cubed beta cubed equals open paren alpha beta close paren cubed, we substitute 1 over alpha cubed plus 1 over beta cubed equals numerator minus numerator b open paren b squared minus 3ac close paren end numerator over a cubed end numerator over open second paren c over a close second paren cubed equals numerator minus b open paren b squared minus 3ac close paren end numerator over a cubed times a cubed over c cubed equals numerator minus b open paren b squared minus 3ac close paren end numerator over c cubed. We alpha squared over beta plus beta squared over alpha. Using the identity alpha squared over beta plus beta squared over alpha equals open paren alpha plus beta close paren dot alpha over beta. Substituting values. Alpha squared over beta plus beta squared over alpha equals open paren minus b over a close paren dot numerator b squared minus 2ac end numerator over c equals minus numerator b open paren b squared minus 2ac close paren end numerator over ac. We are given that alpha and beta are the roots of the quadratic polynomial. Open parent close paren equals a dot x squared plus x plus. Concepts and formulas. Using Vieta's theorem. For a quadratic equation a dot x squared plus x plus equals 0. Sum of roots. Alpha plus beta equals minus b over a product of roots. Alpha beta equals c over a. We use these to evaluate the given expressions. Useful identities. Alpha to the fourth plus beta to the fourth equals open paren alpha squared plus beta squared close paren squared minus 2 open pan alpha beta close paren squared. Alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Alpha squared over beta squared plus beta squared over alpha squared equals numerator. Alpha to the fourth plus beta to the fourth end numerator. Over denominator. Alpha squared. Beta squared. End denominator stepwise solutions. Alpha to the fourth plus beta to the fourth. We use the identity. Alpha to the fourth plus beta to the fourth equals open paren alpha squared plus beta squared close paren squared minus 2 alpha squared beta squared. First, we find alpha squared plus beta squared. Alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Substituting values from Vieta's formulas equals open paren minus b over a close paren squared minus 2 open paren c over a close paren equals squared over a squared minus 2c over a. Now, we calculate alpha to the fourth plus beta to the fourth. Alpha to the fourth plus beta to the fourth equals open paren b squared over a squared minus 2c over a close paren squared minus 2 open paren c over a close paren squared expanding equals to the fourth over a to the fourth minus numerator 4b squared c end numerator over a cubed plus numerator 4c squared end numerator over a squared minus numerator 2c squared end numerator over a squared equals to the fourth over a to the fourth minus numerator 4b squared c and numerator over a cubed plus numerator 2c squared and numerator over a squared 2 alpha squared over beta squared plus beta squared over alpha squared. Using the identity alpha squared over beta squared plus beta squared over alpha squared equals numerator alpha to the fourth plus beta to the fourth and numerator over denominator alpha squared beta squared and denominator we substitute equals numerator b to the fourth over a to the fourth minus numerator 4b squared c and numerator over a cubed plus numerator 2c squared and numerator over a squared and numerator over open second parent c over a close second parent squared equals numerator b to the fourth minus 4b squared ac plus 2a squared c squared and numerator over denominator a squared c squared and denominator equals numerator b to the fourth minus 4b squared ac plus 2a squared c squared and numerator over denominator a squared c squared and denominator we are given the quadratic polynomial open parent close parent equals kx squared plus 4x plus 4 where alpha and beta are its roots and it is given that alpha squared plus beta squared equals 24. We need to determine the values of k. Concepts and formulas using Vieta's theorem for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals k over a using the identity alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with kx squared plus 4x plus 4 equals 0, we get alpha plus beta equals minus 4 over k alpha beta equals 4 over k. Step 2. Use the given condition. Using the identity alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Substituting the given value 24 equals open parent minus 4 over k close parent squared minus 2 times 4 over k. 24 equals 16 over k squared minus 8 over k. Step 3. Solve for k. Multiplying by k squared to clear fractions. 2 4k squared equals 16 minus 8k. Rearrange. 2 4k squared plus 8k minus 16 equals 0. Step 4. Solve the quadratic equation. Dividing the equation by 8. 3k squared plus minus 2 equals 0. Using the quadratic formula, k equals numerator, minus 1 plus or minus square root of 1 squared minus 4 open parent 3 close parent open parent minus 2 close parent and square root, and numerator, over denominator, 2 open parent 3 close parent and denominator equals numerator, minus 1 plus or minus square root of 1 plus 24 n square root, n numerator, over 6 equals numerator, minus 1 plus or minus square root of 25 n numerator, over 6, equals numerator, minus 1 plus or minus 5 n numerator, over 6 equals numerator, minus 1 plus 5 n numerator, over 6 or equals numerator, minus 1 minus 5 n numerator, over 6 equals 4/6 equals 2/3 or equals numerator, minus 6 n numerator, over 6 equals minus 1. We are given the quadratic polynomial, open parent close parent equals 2x squared plus 5x plus c, where alpha and beta are the roots, and they satisfy the equation. Alpha squared plus beta squared plus alpha beta equals 21/4. We need to determine the value of k. Concepts and formulas, using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a. Product of the roots alpha beta equals c over a using the identity alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. So, we can rewrite the given equation as open panel alpha plus beta close parent squared minus 2 alpha beta plus alpha beta equals 21/4, which simplifies to open panel alpha plus beta close parent squared minus alpha beta equals 21/4. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with 2x squared plus 5x plus k equals 0, we get alpha plus beta equals minus 5/2 alpha beta equals k over 2. Step 2. Use the given condition. Substituting into the identity, open panel alpha plus beta close parent squared minus alpha beta equals 21/4. Open parent minus 5/2, close parent squared minus k over 2 equals 21/4. 25/4 minus k over 2 equals 21/4. Step 3. Solve for k rearranging. 25/4 minus 21/4 equals k over 2. 4/4 equals k over 2. 1 equals k over 2. K equals 2. We are given the quadratic polynomial. Open parent close parent equals x squared minus 8x plus where alpha and beta are the roots, and we are given that the sum of the squares of the roots is alpha squared plus beta squared equals 40. We need to determine the value of k. Concepts and formulas, using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a. Product of the roots alpha beta equals k over a using the identity alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with x squared minus 8x plus k equals 0, we get alpha plus beta equals minus numerator, minus 8 and numerator, over 1 equals 8 alpha beta equals k over 1 equals k. Step 2. Use the given condition using the identity alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Substituting the given value, 40 equals open paren 8 close paren squared minus 2k. 40 equals 64 minus 2k. Step 3. Solve for k. Rearranging. 2k equals 64 minus 40. 2k equals 24. K equals 24. Half s equals 12. We are given the quadratic polynomial. Open parent close parent equals 2x squared minus 5x plus 7, where alpha and beta are the roots. We need to find a quadratic polynomial whose zeros are 2 alpha plus 3 beta and 3 alpha plus 2 beta. Concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus a equals 0, sum of the roots alpha plus beta equals minus b over a, product of the roots alpha beta equals k over a. We use these to determine the new quadratic equation. Sum and product of new roots. Sum of new roots. Open paren 2 alpha plus 3 beta close paren plus open paren 3 alpha plus 2 beta close paren equals 5 alpha plus 5 beta equals 5 open paren alpha plus beta close paren. Product of new roots. Open paren 2 alpha plus 3 beta close paren open paren 3 alpha plus 2 beta close paren. Expanding using algebraic identity equals 6 alpha squared plus 4 alpha beta plus 9 alpha beta plus 6 beta squared equals 6 open paren alpha squared plus beta squared close paren plus 13 alpha beta. Using the identity alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. We substitute the known values. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. From the given quadratic equation 2x squared minus 5x plus 7 equals 0. Alpha plus beta equals minus numerator, minus 5 and numerator, over 2 equals 5 halves alpha beta equals 7 halves. Step 2. Compute the sum of new roots 5 open paren alpha plus beta close paren equals 5 times 5 halves equals 25 halves. Step 3. Compute the product of new roots first. Compute alpha squared plus beta squared. Alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta equals open paren 5 halves close paren squared minus 2 times 7 halves equals 25 fourths minus 14 halves equals 25 fourths minus 28 fourths equals numerator minus 3 and numerator over 4. Now calculate the product of new roots. 6 open paren alpha squared plus beta squared close paren plus 13 alpha beta equals 6 times numerator minus 3 and numerator over 4 plus 13 times 7 halves equals numerator minus 18 and numerator over 4 plus 91 halves equals numerator minus 9 and numerator over 2 plus 91 halves equals 82 halves equals 41. Step 4. Form the required quadratic polynomial. A quadratic equation with roots p and q is given by x squared minus open parent sum of roots close parent plus open parent product of roots close parent equals 0. Substituting x squared minus 25 half plus 41 equals 0, multiplying by 2 to remove fractions. 2x squared minus 25x plus 82 equals 0. We are given the quadratic polynomial. Open parent close parent equals 3x squared minus 4x plus 1, where alpha and beta are the roots. We need to find a quadratic polynomial whose zeros are alpha squared over beta and beta squared over alpha. Concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0, sum of the roots alpha plus beta equals minus b over a, product of the roots alpha beta equals c over a. We use these to determine the new quadratic equation. Sum and product of new roots. Sum of new roots alpha squared over beta plus beta squared over alpha. Using the identity alpha squared over beta plus beta squared over alpha equals numerator alpha cubed plus beta cubed and numerator over alpha beta. Using the identity alpha cubed plus beta cubed equals open parent alpha plus beta close parent open parent alpha squared minus alpha beta plus beta squared close parent, and alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Product of new roots open parent alpha squared over beta close parent times open parent beta squared over alpha close parent equals numerator alpha cubed beta squared and numerator over beta alpha equals alpha beta. Substituting the known values. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. From the given quadratic equation 3x squared minus 4x plus 1 equals 0. Alpha plus beta equals minus numerator minus 4 and numerator over 3 equals 4/3 alpha beta equals 1/3. Step 2. Compute the sum of new roots alpha squared over beta plus beta squared over alpha equals numerator alpha cubed plus beta cubed and numerator over alpha beta. Using alpha cubed plus beta cubed equals open parent alpha plus beta close parent open parent alpha squared minus alpha beta plus beta squared close parent, and alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta equals open parent 4/3 close parent squared minus 2 times 1/3 equals 16/9 minus 2/3 equals 16/9 minus 6/9 equals 10/9. So alpha cubed plus beta cubed equals open parent 4/3 close parent open parent 10/9 minus 1/3 close parent equals 4/3 times open parent 10/9 minus 3/9 close parent equals 4/3 times 7/9 equals 28/27. Now numerator alpha cubed plus beta cubed and numerator over alpha beta equals 28/27 divided by 1/3 equals 28/27 times 3 equals 28/9. Step 3. Compute the product of new roots alpha squared over beta times beta squared over alpha equals alpha beta equals 1/3. Step 4. Form the required quadratic polynomial. A quadratic equation with roots p and q is given by x squared minus open parent sum of roots close parent plus open parent product of roots close parent equals 0. Substituting x squared minus 28/9 plus 1/3 equals 0, multiplying by 9 to remove fractions. 9x squared minus 28x plus 3 equals 0. Concepts and formulas. To find the zeros, roots, of a quadratic polynomial and verify the relationship with its coefficients, we use quadratic equation formula z equals numerator minus b plus or minus square root of b squared minus 4ac and square root and numerator over 2a, where the general quadratic polynomial is a dot x squared plus x plus equals 0. Vieta's theorem. If alpha and beta are the roots of a dot x squared plus x plus equals 0, then sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals over a. Stepwise solutions. Find the zeros of open parent close parent equals x squared minus 2x minus 8. Comparing with a dot x squared plus x plus equals 0. A dot equals 1 b equals minus 2 equals minus 8 using the quadratic formula. Z equals numerator minus open parent minus 2 close parent plus or minus square root of open parent minus 2 close parent squared minus 4 open parent 1 close parent open parent minus 8 close parent and square root and numerator over denominator 2 open parent 1 close parent and denominator equals numerator 2 plus or minus square root of 4 plus 32 and square root and numerator over 2 equals numerator 2 plus or minus square root of 36 and numerator over 2 equals numerator 2 plus or minus 6 and numerator over 2 equals numerator 2 plus 6 and numerator over 2 equals 8 halves equals 4 equals numerator 2 minus 6 and numerator over 2 equals numerator minus 4 and numerator over 2 equals minus 2. Verification using Vieta's theorem. Alpha plus beta equals 4 plus open parent minus 2 close parent equals 2 equals minus numerator minus 2 and numerator over 1. Alpha beta equals 4 times open parent minus 2 close parent equals minus 8 equals numerator minus 8 and numerator over 1, 2. Find the zeros of open parents close parent equals 4s squared minus 4s plus 1. Comparing with a dot x squared plus x plus equals 0. A dot equals 4 b equals minus 4 equals 1 using the quadratic formula. Equals numerator minus open parent minus 4 close parent plus or minus square root of open parent minus 4 close parent squared minus 4 open parent 4 close parent open parent 1 close parent and square root and numerator over denominator 2 open parent 4 close parent and denominator equals numerator 4 plus or minus square root of 16 minus 16 and square root, and numerator, over 8 equals numerator, 4 plus or minus square root of 0 and numerator, over 8 equals 4/8 equals 1/2. So, the equation has one repeated root, equals 1/2 equals 1/2. Verification using Vieta's theorem. Alpha plus beta equals 1/2 plus 1/2 equals 1 equals minus numerator, minus 4 and numerator, over 4. Alpha beta equals 1/2 times 1/2 equals 1/4 equals 1/4. 3. Find the zeros of open parent close parent equals t squared minus 15. Comparing with a dot x squared plus x plus equals 0. A dot equals 1 equals 0 equals minus 15 using the quadratic formula. T equals numerator, minus 0 plus or minus square root of 0 squared minus 4 open parent 1 close parent open parent minus 15 close parent and square root, and numerator, over denominator, 2 open parent 1 close parent and denominator equals numerator, plus or minus square root of 60 and numerator, over 2 equals numerator, plus or minus 2 square root of 15 and numerator, over 2 equals plus or minus square root of 15. Verification using Vieta's theorem. Alpha plus beta equals square root of 15 plus open parent minus square root of 15 close parent equals 0 equals minus 0 over 1. Alpha beta equals square root of 15 times open parent minus square root of 15 close parent equals minus 15 equals numerator, minus 15 and numerator, over 1, 4. Find the zeros of open parent close parent equals 6x squared minus 3 minus 7x. Rewriting in standard form, 6x squared minus 7x minus 3 equals 0. Comparing with a dot x squared plus x plus equals 0. A dot equals 6 equals minus 7 equals minus 3 using the quadratic formula. Z equals numerator, minus open parent minus 7 close parent plus or minus square root of open parent minus 7 close parent squared minus 4 open parent 6 close parent open parent minus 3 close parent and square root, and numerator, over denominator, 2 open parent 6 close parent and denominator equals numerator, 7 plus or minus square root of 49 plus 72 and square root, and numerator, over 12 equals numerator, 7 plus or minus square root of 121 and numerator, over 12 equals numerator, 7 plus or minus 11 and numerator, over 12 equals numerator, 7 plus 11 and numerator, over 12 equals 18 over 12 equals 3/2 equals numerator, 7 minus 11 and numerator, over 12 equals numerator, minus 4 and numerator, over 12 equals numerator, minus 1 and numerator, over 3. Verification using Vieta's theorem. Alpha plus beta equals 3/2 plus open parent numerator, minus 1 and numerator, over 3. Close parent equals numerator, 9 minus 2 end numerator, over 6 equals 7/6 equals minus numerator, minus 7 end numerator, over 6. Alpha beta equals 3 half times numerator, minus 1 end numerator, over 3 equals numerator, minus 3 end numerator, over 6 equals numerator, minus 1 end numerator, over 2 equals numerator, minus 3 end numerator, over 6. Concepts and formulas. To find the quadratic polynomial whose roots, zeros, are given, we use the standard form of a quadratic equation. X squared minus open parent sum of roots close parent plus open parent product of roots close parent equals 0, where the sum and product of the roots are given by alpha plus beta equals sum of the roots, alpha beta equals product of the roots. After obtaining the quadratic polynomial, we solve for its zeros using factorization. Stepwise solutions. Given roots, minus 8/3 4/3 step 1. Compute sum and product. Alpha plus beta equals minus 8/3 plus 4/3 equals minus 4/3. Alpha beta equals open parent minus 8/3 times 4/3. Close parent equals minus 32/9. Step 2. Form the quadratic polynomial x squared minus open parent alpha plus beta close parent plus open parent alpha beta close parent equals 0. X squared plus 4/3 minus 32/9 equals 0. Multiplying by 9 to remove fractions. 9x squared plus 12x minus 32 equals 0. Step 3. Solve by factorization. We factorize 9x squared plus 12x minus 32 equals 0. Finding two numbers that multiply to minus 288, 9 times minus 32, and sum to 12. Open parent 18 minus 16 close parent rewriting. 9x squared plus 18x minus 16x minus 32 equals 0. Grouping. Open parent 9x open parent plus 2 close parent minus open parent 16 open parent plus 2 close parent equals 0. Open parent plus 2 close parent open parent 9x minus 16 close parent equals 0. So, the zeros are x plus 2 equals 0 implies x equals minus 2 9x minus 16 equals 0 implies x equals 16 9s. 2. Given roots. 21/8 5/16 Step 1. Compute sum and product. Alpha plus beta equals 21/8 plus 5/16 equals 42/16 plus 5/16 equals 47/16. Alpha beta equals 21/8 times 5/16 equals 105/128. Step 2. Form the quadratic polynomial. X squared minus 47/16 plus 105/128 equals 0. Multiplying by 128 to clear fractions. 128x squared minus 376x plus 105 equals 0. Step 3. Solve by factorization. Finding two numbers that multiply to 128 times 105 equals 13440 and sum to minus 376. Factoring gives 128x squared minus 240x minus 136x plus 105 equals 0. Grouping 8x open paren 16x minus 30 close paren minus 5 open paren 16x minus 30 close paren equals 0. Open paren 16x minus 30 close paren open paren 8x minus 5 close paren equals 0. Z equals 30 over 16 equals 15 eighths equals 5 eighths. 3. Given roots. Minus 2 square root of 3 minus 9. Step 1. Compute sum and product alpha plus beta equals minus 2 square root of 3 minus 9. Alpha beta equals open paren minus 2 square root of 3 close paren times open paren minus 9 close paren equals 18 square root of 3. Step 2. Form the quadratic polynomial. X squared minus open paren alpha plus beta close parent plus alpha beta equals 0. X squared plus open paren 9 plus 2 square root of 3 close parent plus 18 square root of 3 equals 0. 4. Given roots. Minus 3 over denominator. 2 square root of 5 and denominator minus 1/2. Step 1. Compute sum and product. Alpha plus beta equals minus 3 over denominator. 2 square root of 5 and denominator minus 1/2 taking LCM equals minus numerator. 3 plus square root of 5 and numerator over denominator. 2 square root of 5 and denominator minus beta squared equals numerator minus 9 and numerator over 4 beta squared equals 9/4 beta equals plus or minus 3/2. So the roots are 3/2 and minus 3/2, which satisfy the given condition that one root is the negative of the other. We are given the quadratic polynomial. Open parent close parent equals kt squared plus 2t plus 3k, where the sum of the zeros is equal to their product. We need to find the value of k concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals k over a. We are given that alpha plus beta equals alpha beta, thus using the formulas minus 2 over k equals 3k over k, which simplifies to minus 2 over k equals 3. Stepwise solution. Step 1. Solve for k minus 2 equals 3k. K equals minus 2/3. We are given the quadratic polynomial. Open parent close parent equals 4x squared minus 5x minus 1, where alpha and beta are the roots. We need to find the value of alpha squared beta plus alpha beta squared. Concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals k over a. Using the identity alpha squared beta plus alpha beta squared equals alpha beta open pan alpha plus beta close paren. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with 4x squared minus 5x minus 1 equals 0. Alpha plus beta equals minus numerator, minus 5 and numerator, over 4 equals 5/4 alpha beta equals numerator, minus 1 and numerator, over 4. Step 2. Compute alpha squared beta plus alpha beta squared using alpha squared beta plus alpha beta squared equals alpha beta open panel alpha plus beta close paren. Substituting values equals open paren numerator, minus 1 and numerator, over 4, close paren times open paren 5/4. Close paren equals numerator, minus 5 and numerator, over 16. We are given the quadratic polynomial. Open parent close paren equals t squared minus 4t plus 3 where alpha and beta are the roots. We need to find the value of alpha to the 4th beta cubed plus alpha cubed beta to the 4th. Concepts and formulas using Vieta's theorem for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals over a. We use the identity alpha to the 4th beta cubed plus alpha cubed beta to the 4th equals alpha cubed beta cubed open panel alpha plus beta close paren, where alpha cubed beta cubed equals open paren alpha beta close paren cubed. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with t squared minus 4t plus 3 equals 0. Alpha plus beta equals minus numerator, minus 4 and numerator, over 1 equals 4 alpha beta equals 3 over 1 equals 3. Step 2. Compute alpha cubed beta cubed equals open paren alpha beta close paren cubed equals 3 cubed equals 27. Step 3. Compute alpha to the 4th beta cubed plus alpha cubed beta to the 4th alpha to the 4th beta cubed plus alpha cubed beta to the 4th equals alpha cubed beta cubed open panel alpha plus beta close paren. Substituting values equals 27 times 4 equals 108. We are given the quadratic polynomial. Open parent close paren equals 6x squared plus x minus 2, where alpha and beta are the roots. We need to find the value of alpha over beta plus beta over alpha. Concepts and formulas using Vieta's theorem for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals over a. We use the identity alpha over beta plus beta over alpha equals numerator alpha squared plus beta squared and numerator over alpha beta where alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with 6x squared plus x minus 2 equals 0. Alpha plus beta equals minus 1/6 alpha beta equals numerator, minus 2 and numerator, over 6 equals minus 1/3. Step 2. Compute alpha squared plus beta squared using the identity alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Substituting values equals open paren minus 1/6 close paren squared minus 2 times open paren minus 1/3 close paren equals 1/36 plus 2/3 equals 1/36 plus 24/36 equals 25/36. Step 3. Compute alpha over beta plus beta over alpha. Using alpha over beta plus beta over alpha equals numerator alpha squared plus beta squared and numerator over alpha beta substituting values equals numerator 25/36 and numerator over denominator minus 1/3 and denominator equals 25/36 times open paren minus 3 close paren equals minus 75/36 equals minus 25/12. We are given the quadratic polynomial. Open parens close paren equals 3s squared minus 6s plus 4, where alpha and beta are the roots. We need to find the value of alpha over beta plus beta over alpha plus 2 open paren 1 over alpha plus 1 over beta close paren plus 3 alpha beta. Concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0 sum of the roots alpha plus beta equals minus b over a product of the roots alpha beta equals c over a. We use the following identities. Reciprocal sum identity 1 over alpha plus 1 over beta equals numerator alpha plus beta and numerator over alpha beta. Fractional sum identity alpha over beta plus beta over alpha equals numerator alpha squared plus beta squared and numerator over alpha beta, where alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with 3s squared minus 6s plus 4 equals 0. Alpha plus beta equals minus numerator minus 6 and numerator over 3 equals 6/3 equals 2 alpha beta equals 4/3. Step 2. Compute alpha over beta plus beta over alpha using alpha over beta plus beta over alpha equals numerator alpha squared plus beta squared and numerator over alpha beta. First, compute alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta equals 2 squared minus 2 times 4/3 equals 4 minus 8/3 equals 12/3 minus 8/3 equals 4/3. Now, alpha over beta plus beta over alpha equals numerator 4/3 and numerator over denominator 4/3 and denominator equals 1. Step 3. Compute 1 over alpha plus 1 over beta using 1 over alpha plus 1 over beta equals numerator alpha plus beta and numerator over alpha beta equals 2 over denominator 4/3 n denominator equals 2 times 3/4 equals 6/4 equals 3/2. Multiplying by 2. 2 open paren 1 over alpha plus 1 over beta. Close paren equals 2 times 3/2 equals 3. Step 4. Compute 3 alpha beta 3 times 4/3 equals 4. Step 5. Compute the final expression. 1 plus 3 plus 4 equals 8. We are given the quadratic polynomial. Open parent close parent equals x squared plus x plus 45, where alpha and beta are the roots. We are given that the square difference of the zeros is open panel phi minus beta close parent squared equals 144. We need to find the value of p concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0, sum of the roots alpha plus beta equals minus b over a, product of the roots alpha beta equals k over a. Using the identity for the square difference of the roots, open panel phi minus beta close parent squared equals open parent alpha plus beta close parent squared minus 4 alpha beta. Stepwise solution. Step 1. Find alpha plus beta and alpha beta. Comparing with x squared plus x plus 45 equals 0. Alpha plus beta equals minus p over 1 equals minus p. Alpha beta equals 45 over 1 equals 45. Step 2. Compute the square difference formula using open panel phi minus beta close parent squared equals open parent alpha plus beta close parent squared minus 4 alpha beta. Substituting values. 144 equals open parent minus p close parent squared minus 4 open parent 45 close parent. 144 equals p squared minus 180. Step 3. Solve for p. P squared equals 144 plus 180. P squared equals 324 equals plus or minus 18. We are given the quadratic polynomial. Open parent close parent equals x squared minus x plus k, where alpha and beta are the roots. We need to prove that alpha squared over beta squared plus beta squared over alpha squared equals p to the 4th over q squared minus numerator 4p squared and numerator over q plus 2. Concepts and formulas. Using Vieta's theorem, for a quadratic equation of the form a dot x squared plus x plus equals 0, sum of the roots alpha plus beta equals minus b over a, product of the roots alpha beta equals k over a. For our equation x squared minus x plus k equals 0, we have alpha plus beta equals p, alpha beta equals k. We use the identity alpha squared over beta squared plus beta squared over alpha squared equals numerator alpha to the 4th plus beta to the 4th and numerator over denominator alpha squared, beta squared, and denominator. Also, alpha to the 4th plus beta to the 4th equals open parent alpha squared plus beta squared close parent squared minus 2 alpha squared beta squared, and alpha squared plus beta squared equals open parent alpha plus beta close parent squared minus 2 alpha beta. Stepwise proof. Step 1. Compute alpha squared plus beta squared using alpha squared plus beta squared equals open paren alpha plus beta close paren squared minus 2 alpha beta. Substituting alpha plus beta equals p and alpha beta equals k. Alpha squared plus beta squared equals p squared minus 2q. Step 2. Compute alpha to the fourth plus beta to the fourth. Using alpha to the fourth plus beta to the fourth equals open paren alpha squared plus beta squared close paren squared minus 2 alpha squared beta squared. Substituting alpha squared plus beta squared equals p squared minus 2q and alpha squared beta squared equals k squared. Alpha to the fourth plus beta to the fourth equals open paren p squared minus 2q close paren squared minus 2q squared. Expanding equals p to the fourth minus 4p squared k plus 4q squared minus 2q squared. Equals p to the fourth minus 4p squared k plus 2q squared. Step 3. Compute numerator alpha to the fourth plus beta to the fourth and numerator over denominator alpha squared beta squared and denominator alpha to the fourth over beta to the fourth plus beta to the fourth over alpha to the fourth equals numerator alpha to the fourth plus beta to the fourth and numerator over denominator alpha squared beta squared and denominator. Substituting alpha to the fourth plus beta to the fourth equals p to the fourth minus 4p squared k plus 2q squared and alpha squared beta squared equals k squared. Equals numerator p to the fourth minus 4p squared q plus 2q squared and numerator over q squared. Splitting the terms equals p to the fourth over q squared minus numerator 4p squared q and numerator over q squared plus numerator 2q squared and numerator over q squared. Equals p to the fourth over q squared minus numerator 4p squared and numerator over q plus 2. Thus, we have